Okay, so this is one possible way that we could demonstrate the approximate percentage of oxygen in the air. So what I've got here is two gas syringes, here and here. This is all sealed together, so if I push this side in, what you should see is this side at the moment comes straight out, and similarly if I push this side in, this one comes straight out. So it's worth just checking that that all works before we start this experiment, because if there's a problem and it's not sealed properly, then the results can be invalidated, like so. Okay, so I've just started with 100 centimetres cubed of air in this gas syringe and 0 in here. You might want to think about the limitations of this, because this of course assumes that that's 100 centimetres cubed but discards all of this volume in between, so that's a little bit dodgy in terms of the results, but that's a procedural error that you could always discuss in an evaluation section. But starting with 100 is quite a nice round measurement to start here. Inside this tube there's copper metal. I don't know if you can see this, but this is pinky brown shiny solid in the centre of there at the moment. Now copper metal is not very reactive, but if you heat copper strongly in the air, it will react with oxygen. So I've set this up carefully to make sure that there's an excess of copper turnings in there, and also that the turnings have been used. Perhaps you could have a think about why we need to have an excess of copper, and also why copper turnings and not just one big block of copper is being used. Have a think about that, pause it whilst you're thinking. So the reason it's important to have the excess of copper is to make sure that all of the oxygen in this air, in the volume of air within this apparatus, is removed by reacting with the copper. And the turnings have a much higher surface area, and therefore this reaction will happen much quicker with the turnings present. So in a moment I'm going to start heating the copper. Importantly, the copper will react with the oxygen gas to produce a solid, and the solid that it's producing is copper to oxide. So if I can find a pen which will work on the board up here, we start with Cu solid and O2 gas producing CuO solid, and if I wish to balance that equation, there's 2 oxygens here, so we need 2 oxygens on this side, so multiply that by 2. That gives 2 coppers here, so 2 coppers needed over here. But importantly, the gas oxygen becomes, if you like, locked up as a solid over here. And so the copper oxide removes that volume of gas from the air and leaves behind any gases in that air mixture that were not oxygen. So I'll come back over here and I'll just start to heat this reasonably strongly, but I don't want to heat one part of that tubing for too long, because the tubing might melt and get a hole in it and then I have to stop. I'm also going to try my best not to catch the rubber tubing so that it doesn't set on fire. So I'm going to hold that with my left hand and just carefully pass the gas, the air mixture, over that copper like so. And I'm just going to move the Bunsen burner across, up and down this copper, up and down the copper here, to try to just make sure that it's all heated uniformly. So if I just keep doing that, I'm going to have to keep swapping hands so that I can push the gas syringe across. And perhaps you might start to see already that some of this copper is starting to change colour. And as that copper changes colour, it's forming the copper oxide. So copper oxide is a black solid, and it should mean then that that nice pink, brown, shiny solid of copper, which we started with, turns into a solid with a dull coating of black, fire there, never mind, black copper 2 oxide. Try and keep that away from the rubber bud. Let's keep that moving. It's nice and warm now. Just keep moving that backwards and forwards. So you get the general idea. So the copper is reacting away the oxygen from that mixture of gases. And as I continue to pass this gas backwards and forwards, what you might be able to see is that the volume of gas in the apparatus is dropping each time. So if I just push this back one more time, backwards and forwards, that's probably hot enough, so I'll just stop heating that now. Let's keep that going backwards and forwards a couple more times, trying not to break the glass inside that tubing at the moment because it's quite hot. So just keep passing that gas backwards and forwards. and hopefully you can see that the remaining volume on the gas syringe is lower than it was before. Right, it's important to let this all cool down to room temperature again before recording the final volume of gas. Perhaps think about why that matters. So gases will expand when they get hotter, and so if the gases are above room temperature, then they would have expanded up. Now I can see right now, if I have a look on this scale here, after allowing that to cool, that the final volume is something like 93 centimetres cubed, which is quite a bit higher than I would have expected it to be. So at that point, that makes me wonder whether I ought to just heat this a little bit longer and try again. So it's good practice to heat again and to continue to pass that gas backwards and forwards until there's no further change. And that's just a way of making sure that all the oxygen has reacted away. So if you suspect that some oxygen still remains in that sample, just repeating the heating and allowing that gas to pass across that hot copper a couple more times until you get a constant final volume is a good way to just double check. And right now it does seem to be removing more of that. Even at the hot temperature here, we've got 90 centimetres cubed of gas remaining. So you carry on with that until you've got no further change, heating and cooling, just passing that gas backwards and forwards. But as observations go, that's about as exciting as this one's going to get. So I'm going to stop there, and you can use the information in your lab book to fill in your results.